Awesome. So thank you for that introduction. I'm so excited to talk to you today about some really cool work that myself and my wonderful collaborators and my advisor, Justin Su, have been working on over the past few years, symbolic execution for randomized programs. So it's the afternoon. Let's try to wake everybody up a little bit by doing a classic brain teaser. So you are on a game show and there are 3 identical doors in front of you, and behind 2 of the doors are sheep, and behind 1 of the doors is the one ring to rule them all. And the host asks you to pick a door that you think the one ring is behind. And you pick 2, and then after you've chosen your door, the host will open a door containing a sheep randomly if he has a choice. So then the host asks whether you want to swap your chosen door to the remaining closed door. And the question becomes, should you swap? Yes, I see a thumbs up, and that is correct. You should always switch doors in this case. In fact, you will win the one ring 2/3 of the time if you switch doors, regardless of your initial door choice, which is somewhat perplexing at first sight. So let's take a step back and think about why this might be true. So one way of kind of working through this is kind of a pen and paper approach where we diagram all the possible choices we could make through the game show. So at the beginning, you might choose door 1, 2, or 3 as the contestant. And the one ring will be uniformly, randomly behind door 1, 2, or 3, regardless of what choice of your door you initially picked. The host then will open a sheep door and randomly, if he has a choice. Now, because we've annotated some probabilities here of like what door the one ring is behind and what door the host opens, we can just multiply it across and we can get the probability of each outcome happening. Then we can say, okay, a green check mark says you've won the one ring, and the red X means you won a sheep. I mean, I would still be happy with a sheep, but and we can say, well, what's the outcome if you kept your original door versus whether you swapped your original door? So we can, color code these depending upon what door you originally chose as red, blue, and green, for example. And we want to prove this property that you will win the one ring 2/3 of the time if you swapped your doors. So we can highlight the outcomes that we're interested on, and we can add the probabilities together, and we can see regardless of what door you chose, you'll win the one ring 2/3 of the time if you swapped your door. Great. Now, is this good enough? Is the pen and paper approach good enough for us? Well, actually, Paul Erdős famously didn't believe this on using decision trees until he was shown a Monte Carlo simulation of the Monty Hall problem, and then he was convinced. So obviously, we can do that. We can write a program to represent the Monty Hall problem, and we can run it and all that wonderful stuff. But as PL people, we might want a formal, principled approach that maybe applies the techniques that we use on the pen and paper in a more formal way. Now, we see a tree here. If only there was some technique that we could maybe make this tree automatically. As you might have guessed, symbolic execution to the rescue. So, how many of you have heard of symbolic execution before? Good chunk of you. So it's pretty simple. So you got this function foo here, and there are kind of 2 key ingredients to symbolic execution. A sigma map, which maps program variables to symbolic expressions, and phi, which is a Boolean formula representing constraints on the symbolic variables that must be true at a specific point in time. So at the very beginning of this program, we first take in an argument x, and we assign x a fresh symbolic variable alpha, and store that in sigma. And of course, there are no constraints on what alpha can be because we just started the program. So we can go through the program and say, okay, well, z is assigned x times 2. Symbolically, that means z is now 2 alpha, as x is alpha. And at branches, we say if z is equal to 32, go inside the loop and crash, or if it's not, print OK. So in symbolic execution, we traverse both sides of the branch and we store the guard in a symbolic form in the path condition. So on the left-hand side, it will crash if 2 alpha is equal to 32. So what if we wanted to do this on randomized programs? Well, a good symbolic execution technique for randomized programs will have kind of 3 key challenges that we have to solve before we can do this. First up, and most obviously, is we need some way to handle random sampling statements. Because this is, a new type of statement that doesn't appear in normal programs, if you will. So on the first line here, if you can't see it, it samples, it picks a random door between 1 and 3 to put the 1 ring behind. The second problem is this property that we wanted to prove is a quantitative property. It says that you will win the 1 ring 2/3 of the time if you switch doors. Normal symbolic execution is principally concerned with whether you will reach an error instead of how often maybe an error occurs or how often some good thing happens. So we need some way to talk about quantitative probabilistic properties. Lastly, a natural question that we want to ask with probabilistic programs is handling unknown inputs. With the Monty problem, it took in a choice of door, and it took in a Boolean variable that decides whether to switch doors or not. So we want to be able to prove this property from before, regardless of your initial door choice, or for more fun programs like differential privacy for all databases, for all delta and epsilon, etc. Okay. So our problem that we want to solve is how do we perform symbolic execution on randomized programs so that we can verify quantitative properties with for all unknown inputs. Okay, so our contributions are naturally, we have a solution for that problem. We have a prototype implementation, PLINKO, that is built upon the KLEE symbolic execution engine, which allows us to perform symbolic execution on real-world programs as KLEE takes in LLVM bytecode. So like C, C++ programs that would normally have like a RAND statement in it. And then lastly, we have a comprehensive evaluation on a custom set of case studies from the randomized algorithms literature. And we also compare against 2 state-of-the-art general purpose tools for analyzing and proving properties of probabilistic programs. And I'll show what those are later in the talk. Okay, so now let's talk a little bit about the actual solution, the fun part, and what you're probably all here to listen about too. So there are kind of 3 main system components to our technique. First up are probabilistic symbolic variables, which is intuitively a new class of symbolic variable that represents the results of random sampling statements. From these, we build on top of that to compute the probability of branches and whole path of programs. Back in the little tree that we drew, we had the probability, and that was a crucial part of actually being able to prove the property that we wanted to prove. And then lastly, how do we actually take these probabilities and verify that the property is true? Well, we encode the correctness property as an SMT query. And I'll talk about each of these 3 in turn. So first up, we've got this tiny little program that takes in a guess. We're going to constrain it between 1 and 6. It rolls a fair die, fair 6-sided die, and will return true if your guess is correct and false if not. So in normal symbolic execution, we assign guess alpha, which is a normal run-of-the-mill standard symbolic variable, and it represents an unknown program input. Random sampling statements are also a form of unknown input in a way, except that we know it's distributed across a certain unknown distribution. So we make a new class of symbolic variable, which we distinguish as probabilistic symbolic variables. So we assign on a random sampling statement, we assign role delta, and delta represents the result of a random draw. So in general, in this case, we create a fresh symbolic variable, delta, for the program variable role, and then we also record the distribution from which role is distributed from. And we store that in a new piece of symbolic state called P, which maps probabilistic symbolic variables to distribution expressions. So in this case, delta we know is a random integer, uniform random integer between 1 and 6. Okay, so let's make our tree again. So we have guess is assigned alpha at the very beginning. Then we assign role to be delta, and we record the distribution. And then we branch on the outcome and code the path condition as on the left, alpha is equal to delta, meaning that it will turn true, and alpha is not equal to delta, meaning that the function returns false. Okay, this is all well and good. Now, there's something missing. Naturally, we want to be able to say what is the probability that one branch is executed over another. Clearly, for this example, the right-hand or false branch should be executed approximately 5/6 of the time versus the left-hand side or the true branch, which is 1/6 of the time. And we would like to automatically compute these probabilities. So, to gain some intuition on how we do this, let's consider the case where we just have normal run-of-the-mill standard symbolic variables. So we have this function bar, takes in an x, does some stuff, and then it branches on whether x is greater than 5. So making our doing the same thing as before, we let x be alpha, and we set the path condition to just be top because there are no constraints on alpha. Now we do some stuff, and now we branch on whether x is greater than 5. So we have the branches as before. So what is the probability that alpha is greater than 5? Well, we don't know what alpha is, and we don't want to assume anything about alpha. We don't want to assume that it's from a distribution or really anything. But we do know that on a given execution of the program, either it will be true, either alpha will be greater than 5, or alpha will be less than or equal to 5. So one branch will be executed with probability 1, and one branch will be executed with probability 0. To encode this idea, we use Iverson brackets. So Iverson bracket, if you haven't seen, is it takes a predicate P, it will turn 1 if the predicate is true, and 0 if the predicate is false. So the probability that alpha is greater than 5 is simply the Iverson bracket that alpha is greater than 5. And the same for the false branch. Okay, hopefully we're all on the same page and it's relatively simple here. So now let's consider a general case where we do some stuff and we have a path condition phi where at this point of the program and phi is true. And then we branch on C. Well, we branch on C. Now I want to distinguish that C is a program expression using program variables, and C-sim is the symbolic expression equivalent to C, but over symbolic variables. So again, what's the probability of one branch being executed over another? Remember that phi contains all the constraints on the symbolic variables that must be true to reach this point in the program. And then we want to know what the probability that C-sim is true, given that we are already at this point in the program. Now, if this is sounding somewhat familiar, this is actually just the conditional probability that C-sim is true, given that phi is true. And the negation is on the opposite side as well, or 1 minus the true branch is another equivalent way of saying this. So a standard transformation or definition for conditional probability is the probability that C-sim given phi is just the probability that C-sim is true and phi is true over the probability that phi is true. And we use this formula to compute the the probability of a branch happening. So let's return to our guess roll function here. And we've got phi to be top, and we've got our path that we're more concerned about right now, that alpha is equal to delta. And we want to know what the probability of that being true is. of that path going occurring. So P, as we saw in the previous slide, is equal to the probability that alpha is equal to delta over the probability of top. So how we do this is we have this massive sum, and you don't have to fully understand all the math behind the summation, except really what we're doing is we're counting the number of assignments to delta that satisfy alpha equals delta. And we're building up a formula that encodes this count. So to make this a little simpler, let's expand the sum out. So we have this sum of 6 Iverson brackets that if you had an assignment to the universal symbolic variable alpha, it would return the probability that that branch is true, or that branch occurs. So if alpha was 1, clearly the numerator would equal 1, and the denominator will always equal 6. So again, I want to stress that this is a symbolic formula or expression for the probability of a branch. Okay? The last key component here is how we deal with proving these properties. So the property that we wanted to prove again was you want to win the one ring 2/3 of the time if you switch doors, regardless of your initial door choice. So there are a few different parts to this property. The first property, the first component rather, is a predicate psi, which is ultimately kind of like a filter on the tree that we're building up with symbolic execution. So we're saying you will win the one ring if you switch doors. So we encode that as a predicate psi over the symbolic variables, where beta, if you recall, is the symbolic variable attached to whether you're going to switch doors. When we're saying that that's true, you're going to switch doors, and then you're going to win the one ring, aka the function returns true. The second component is a target probability bound function f. In this case, it's just 2/3. It's ultimately what probability we want to prove is true, that the program satisfies. Really, what's the probability of the predicate psi occurring should it be somehow related to this target probability bound function over the symbolic variables. Third part is a binary relation, which we're saying the probability is 2/3, but in general it could be less than, it could be an upper bound, lower bound, etc. And then lastly, and this is the part that we get from the symbolic execution part, the probability that psi happens, or the probability that you will win the one ring if you switch doors. And we can get that from all the different paths from the symbolic execution tree. And don't worry too much about the actual form of that. It's just from the tree. So all in all, the property that the SMT query that we want to validate is for all settings of alpha and beta, the probability that the program you will win the one ring, given that you switch doors, is equal to 2/3. In general, it's in this general format, and we can really support any property that can fit into this general format. Okay, so we got an implementation. We call it PLINKO, and it's, like I said before, it's built on top of the KLEE symbolic execution engine, which allows us to work on the level of LLVM bytecode. So we're interested in real-world randomized programs. So you might have your C program here, you compile it in Clang to get your LLVM bytecode, you throw that to PLINKO, and we perform the symbolic execution of that program to get that tree with the probability annotations on it. You also provide the SMT query that we talked about on the previous slide, which we then ship off to Z3 to have Z3 try to invalidate or refute our query, thus proving the property in question. Okay, so we have this implementation, we have this technique. How well does it work? So to evaluate our technique, we are principally concerned with two questions. How efficiently can PLINKO verify probabilistic properties on complex real-world programs? And secondly, how does PLINKO compare with other general-purpose approaches? So for our evaluation, we compared against the psi solver, which is an exact probabilistic inference engine for probabilistic programs, and STORM, which is a probabilistic model checker. So first up, let me talk about the first question, where we want to know how well does PLINKO work in general. We constructed a series of a few case studies from the randomized algorithms literature, including Bloom filter, Countman sketch, which are probabilistic data structures, Freivalds algorithm, reservoir sampling, a monotonicity testing function from the property testing literature. And we have a bunch of statistics here, and I want to stress that the case studies are written in C++. And on the very right, we have a list of concretizations. By concretizations, I mean variables that are directly related to loop bounds or the sizes of input arrays as KLEE and symbolic execution in general. In order to perform a full path exploration, we need to set these, because otherwise KLEE will essentially concretize them in the background, and we won't really know what they are. So the big takeaway message that I want to say here is that we were able to verify the properties for all of these, except for Bloom filter, because of a bug that we found in the open source implementation that we used. And we did so all within 10 minutes, and those are the highest concretizations that we were able to do so. Secondly, most of the time that we spent was on the constraint solving, which seems to suggest that that is the main bottleneck here. And we can talk more about that offline if you're curious as why that might be. To compare against Psi now, I want to talk a little bit about how the different representations of PLINKO versus Psi to better understand that this comparison makes sense. So Psi takes as input a Psi program, which is a probabilistic program with discrete and continuous random variables and sampling, observed statements, all of the fun stuff that we all know and love. And it will output a symbolic representation of the joint posterior distribution on the outputs. So essentially, Psi will get us our encoding of Psi that we're concerned about, that we use symbolic execution to create. And then we kind of do the same thing where we ship off the property to an SMT solver, Z3, in the same way that we do it before. So we imported some of our examples over into the Psi world, and we have some performance results. So blue is the normal version of PLINKO, and you can see Psi really beats us here. But if we add in some very simple algebraic simplifications into the PLINKO's engine, that, like associativity, commutivity, distributivity, when we manipulate the symbolic expressions and Psi, we can see that we're actually 55% faster than Psi. And the x-axis here is basically a concretized parameter that increases the size and complexity of the program and the property that we wish to verify. For monotone testing, again, the x-axis is the setting of the concretized variable that increases the size and complexity of the program. And we can see here that PLINKO just scales really infinitely better than Psi in this regard. Like it's a lot better. And then reservoir sampling, again, the variable on the x-axis is a concretized parameter, and orange is Psi, and blue is PLINKO. For small concretizations, it's roughly equal, but in general, PLINKO scales better. For STORM, STORM is a probabilistic model checker for finite state probabilistic transition systems. So we ported a couple of our case studies as Markov decision processes, and we said, okay, STORM, verify the property for us. Now, PLINKO performs a universal quantification over all inputs of a given data type, like an integer. This is not a feature that STORM has. Instead, the equivalent is a non-deterministic choice over a fixed finite domain. So we had to limit the domain for STORM. If we limited for Freivalds' example, every element can be 1 or 2, it could verify the property in 3 seconds. When we increased this to 3, it took 14 hours before we had to terminate the experiment. So In comparison, PLINKO could verify the property over all 32-bit integers in 75 seconds. So in general, PLINKO can efficiently and effectively verify quantitative properties on a variety of real-world programs over all unknown inputs, and it generally beats more general-purpose tools in performance and expressibility. So in conclusion, we have a symbolic execution method for randomized programs to prove quantitative probabilistic properties over all unknown input parameters. We have a prototype implementation that is available freely and open source on Zenodo that you can check out on our case studies. And then we have an evaluation of a set of case studies, which is also open source that you can take a look at yourself. And that is it. There's plenty more in the paper. I won't go into detail, but I'm happy to talk about anything offline. And thank you, and I'll take any questions.
Thank you. Thanks for the nice talk. Great choice of font too. Very nice. Yeah, there's already a question.
Yeah, so the expression Iverson bracket, during execution, do you have to maintain it symbolic or concrete? How do you compute that concretely? Is it approximate? Numerical?
So we represent the expression in a symbolic form, and we send the entire expression over to Z3 because Z3 the expressions are over the universal symbolic variables, and the target probability bound that you might want to prove might be in terms of these symbolic variables. So we don't right now do any types of simplifications except in some small cases. We do have some optimizations on these symbolic expressions to, say in the case of that dice roll, we can compute it like 1/6, but we do maintain a symbolic form for them.
So Z3 has no axioms for those key Iverson brackets. So how do you do that?
We represent them as an if. So if alpha is greater than 5.
You can do for discrete domain.
Correct. We only are really concerned with discrete domain here and uniform or like Bernoulli transformations as, we're more concerned with these types of randomized algorithms that use like RAND or something like hashing or sorting algorithms or things like this. So the restriction to this discrete domain isn't restrictive for the types of examples that we want to prove.
And it has to be countable and timing.
Correct.
That already kind of answers my question. But cool work. Thanks for the talk. But maybe could you see that your approach can also be applied to programs where you draw from continuous distributions, or is there a real hard limitation there?
The tricky thing with that is, the general approach of performing with the probabilistic symbolic variables would work for continuous variables. The tricky thing is how do we compute the probabilities in a symbolic manner? So one future work idea is maybe to leverage the power of psi and kind of fuse these two approaches to have psi do some inference instead of building up this big expression. But currently, no, we don't support continuous functions.
Thanks for the talk. So you primarily framed symbolic execution in this work as a method for verification. I was wondering if you could compare it to symbolic methods for exact inference on probabilistic programs that use representations like BDDs and similar tools.
Yeah, that was actually something we kind of explored a little bit. Like there was some prior work, like the DICE paper that performed exact symbolic inference. And there is some, I think there is something there that we could leverage some of the techniques that they used with BDDs. Just in terms of the timing, we didn't get something like that working, but it is something that we're interested in doing as we do fully understand like the limitation of how we compute the path probabilities. But I want to just kind of put in a comment that, even with this, we're able to, verify examples that currently have not been done automatically with the state of the art, at least not at the scale that we can do. But definitely, that's something that we're actively looking at.
I guess I was mainly just wondering very briefly if there are advantages of of just doing it for verification as opposed to doing it for inference, or perhaps vice versa, that give you an advantage or a disadvantage.
I think they're complementary problems. I don't know if I could say like one is better or worse. I think ultimately like these can be, they are similar. The fact that Psi, can compute essentially what we are doing, but in a different way, and they're performing exact inference using simplification rules as opposed to like BDDs. So I think they're related, and I think that should be studied a little bit more on how exactly we could maybe fuse these two approaches.
Thank you.
Mm-hmm.
You alluded to these algebraic rewrite simplifications that you did. Can you just say a little more about that? What types of equations do you use and where do they show up?
Yeah, so the algebraic simplifications, you might have a path condition like, let's see, when you apply the substitutions for your probabilistic symbolic variables, when you're computing the sum, you might have some terms, like you might have like 1 plus, you might have like delta plus 5 is equal to 6. Well, delta, when say delta is like 1, well then 1 plus 1 is equal to 6, we know that that's false. So like that type of algebraic identities, we try to pre-compute and simplify these down using like De Morgan's law and all these Boolean identities, as well as more arithmetic identities. And this is something that Psi does just natively, so.
Oh, yeah.
Yeah, okay. I will ask a final mean question. So this is a, let's say, forward approach, right? You're starting the program, you're executing it symbolically forward. Are you aware with these weakest pre-expectation calculi, or are you aware of them?
Yes.
Can you compare? Not in terms of tools or anything, but when is this more advantageous than doing these WP computations?
Yes. So I'm not the best source for a weakest precondition. That definitely leans more on my advisor, or actually a co-author might have a better explanation than I do for this. But we can take this offline if you would like.
Maybe when we set up the next.
Yeah.
I think.
So I think it's a derivative system, so you would need something like looping variance or things to here. Yeah. So we have some work around those lines also, where we try to figure out the looping variance. The great part about symbolic execution is you completely sidestep this problem of finding out looping variance.
And then you execute forever.
We execute forever, but then, like for example, the question on verification, so you can always get word wrongs. And we just sum, right? So you may not even have to compute the actual expression, but you can still verify that it's not.
Unless soundness for you means over approximating. Then it's not sound.
So you look at the complementary thing then.
True. Yeah. Okay, thank you. Then let's thank Zachary again. Very nice.